Hello and welcome to the YouTube channel Decreations Resources. We are looking at some topics from mathematics, especially linear algebra, and today we are going to look at the concept of row echelon form of a matrix. Now, before we understand what that form is, let us know what is the reason why we should study it. So, are there any applications of this form? Indeed, yes. If you want to solve linear system of equations, you will need this form. Also, to find the rank of a matrix. Now, we will be solving a system of equations later, so you would understand how exactly this form is used. Now, how do you get this form? So, there will be a matrix. All of you are aware that matrix is basically an array of numbers. There are rows, there are columns, etc. And this matrix, we are going to convert it to row echelon form by applying row operations. We have done several videos on matrices and we've also talked about row operations. We know that interchanging the rows or multiplying by a constant or adding another row to that row, etc. are some examples of row operations, and it's basically Gaussian elimination that we are doing. So when you do that on this matrix, you get a matrix of row echelon form. But how do you know that you've got that form? Well, there are certain characteristics that you should remember. For example, all 0 rows have to be at the bottom of the matrix. So if there is a row which contains only 0 as the elements, it has to be at the bottom. Then the first non-zero entry of each row. So it's also called a leading entry for the obvious reasons, or it's also called a pivot. That has to be to the right of the leading entry in the row above it. So we'll see it once we are actually using a matrix, because this explanation you may not be able to visualize it immediately. But basically imagine that there are rows and columns and there is one entry here. So we are saying the first non-zero entry in each row. So if you consider the next row, and if this is the non-zero entry, it has to be to the right of the leading entry of the row above it. Also, all elements below a leading entry are 0. Let us see an example to understand it better. So see this matrix. Now, is it a row echelon form? It is not. Can you give one reason? Well, we have seen that all elements below a leading entry need to be 0. Here you will see that in the first row, this 1 is the leading entry and you have non-zero elements here. So in order to get a row echelon form, you will have to make these two numbers 0. Also, if this is the leading entry in the next row, you will have to make this number 0 as well. So let's try to do it, and we are going to do row operations. So let's focus here. We want to make these two entries 0. We'll start with the first column from the third row. Here it is minus 1. Now if you want to make it 0, what will you do? It's obvious. If you are going to add row 1 to row 3, you will see that the numbers will cancel and you will get here 0. So let's simply add row 1 to row 3. So minus 1 will become 0. Now this doesn't happen to only the single entry in the row. If you're adding, it happens to all the entries. Now understand here that if we are adding row 1 to row 3, the only change is going to happen is in row 3. Row 2 obviously is going to remain unchanged, and row 1 will also remain unchanged. It's just being added to row 3. So whatever changes take place are supposed to take place here in row 3. So minus 1 has become 0. Now 2 plus 1 is 3 and 2 minus 1 is 1. So this is how it is going to look. But still, we have this number which is non-zero, and it is an entry which is below the leading entry, so it has to be 0. So we need to make it 0. So how do you do that? Well, we will add minus 2 into first row, or in other words, we can also say that subtract 2 into first row, whichever way you want to say it. So 1 into 2 is 2. So 2 minus 2 will give you 0. Now here it is minus 1. So minus 2 into plus 1 is minus 2. So minus 1 minus 2 is minus 3. and this is minus 1 into minus 2 is plus 2. So 1 plus 2 is 3. So you will see that as expected, the changes that are happening are in row 2. So you can see that it has changed to 0, minus 3, 3. Row 1 remains unchanged, row 3 remains unchanged as well. Now what is the next step? Now we want to make this entry 0. So how will you do it? Well, you can see row 2 and row 3, and you can see that simply if you add row 2 to row 3, 3 minus 3 will give you 0. So let's do it. So 0 plus 0 is 0. 3 minus 3 is also 0, and 1 plus 3 is 4. So this is how the matrix is going to become. And now if you just divide the second row by by 3, and if you divide the third row by 4, this is what you are going to result in. Is this a row echelon form? Yes, it is, because you can see that, well, there is no 0 row here. So had it been, it should have been at the bottom. You can see that the leading entry is to the right. So this is the leading entry, it is to the right of this. This is the leading entry, it is to the right of this. And all the entries below 1 are 0. Or in this case, this is the leading entry. So the entry below this is again 0. So we have actually reached this matrix, as you can say, is an example of row echelon form. Now you would ask, why, what was the application? I had mentioned something about system of linear equations. So let's see, actually when you are doing this, you are indirectly solving a system of equations. So only thing right now what was missing was what is there on the right hand side. So let us quickly see a system of equations. Let's say that this is the system of equations. We formulate a coefficient matrix, and usually we can augment it with the entries on the right hand side. So let's say that this is augmented. So see this matrix: 1, 1, minus 1, 2, minus 1, 1, minus 1, 2, 2. If you see previously, same matrix we had obtained: 1, 1, minus 1, 2, minus 1, 1, minus 1, 2, 2. Now what we are saying is, we will perform the same operations, row operations on this matrix, and reach the row echelon form. But it will not happen to the left hand side entries alone. It will also happen to the right hand side entries. Actually, I could have just augmented this and performed the operation simultaneously. But since you were learning it for the first time, I didn't want you to get confused. So I did not do it that time. But you can tally, you can perform the same operations 1, 2, 3, 4 on the right hand side as well. And if you perform these operations simultaneously, when this matrix is going to this matrix, the right hand side entries are going to this. So you must have seen that, see, it's parallel. How we eliminate entries in order to solve system of equation, we are doing the same thing, but with matrices it becomes much easier. And now if you try to put it back to the form of the equations, you will see that this is x plus y minus z, because here there would have been a column vector x, y, z. These set of equations, you could have written it as this matrix into the matrix 3 by 1 matrix x, y, z is equal to the 3 by 1 matrix minus 2, 5, 1. So the equations that we get are x plus y minus z is minus 2. Then here you can see it's 0. So there won't be any entry with x here. Y minus z is minus 3. And here you can see that x as well as y is 0. And this is the last entry. So z is 2. Now if z is 2, you can just back substitute and understand that y has to be minus 1 and x has to be 1. You can put in those numbers and cross check. See, if you put minus 1 here and it's 2 here, so this will give you minus 3 and so on and so forth. So what have we done? We understood how a row echelon form looks, and we also used it for solving a system of equations. So we also immediately saw an application of this. Okay. So further we will see some more concepts related to this. There is also row reduced form that we are going to talk about later. We'll stop for now. Keep watching the further episodes. Thank you.